Since photons are particles of light, that must mean that they are traveling at the speed of light. This makes them truly relativistic particles. Because of this, the equation that we use for macroscopic objects do not hold up when they're trying to describe the momentum of a photon. Instead, we need to use our relativistic equations for energy and momentum. Photons are never at rest. They are always moving at the speed of light. Even collisions with electrons do not cause them to stop moving. Instead, all of the energy that was carried by the photon is transferred to the electron, and the photon simply ceases to exist. Remember that we can describe the momentum of any particle. Say we have a particle that is moving very slowly compared to the speed of light, say 100 meters per second. This divided by the speed of light gives us a very small number, and that subtracted from 1 really gives us just 1 in our denominator, leaving us with the equation for macroscopic objects. When we are talking about a photon, the velocity of this particle is the same for the speed of light. Since those two velocities are equal, we can replace all of the expressions for velocity in our equation with the speed of light. The speed of light divided by the speed of light gives us a value of 1. So that last term down there becomes 1. 1 minus 1, square rooted or not, makes the denominator in our equation equal to 0. Dividing by 0 gives us an infinite momentum. So if our photon has mass, then the momentum of that photon is equal to infinity, and that can't be right. Since the momentum cannot be infinite, then the mass of the photon has to be 0. This actually makes sense since we know that the photon is always traveling at the speed of light and can never be at rest. Now we also know that the energy carried by a photon is equal to Planck's constant times the frequency of the vibration of our photon. We also know that the momentum of a photon must be obtained from the relativistic formula. We just decided that the mass of the photon is 0, so we can get rid of that last term. Now there are a lot of superscripts here, so let's square root both sides. This gives us the energy of the photon is equal to the momentum of the photon times the speed of light. Well, we are mostly interested in the momentum of the photon, so let's rearrange for that. So the momentum of a photon is equal to the energy of the photon divided by its velocity. Since energy is the frequency of oscillation times Planck's constant, we can also represent the momentum with these variables. But also remember, we know that the velocity of a wave is equal to the frequency times its wavelength. So we can substitute that in our denominator, cancel out the frequency, and end up with an expression for momentum that relates back to the wavelength as well. So calculate the momentum of a visible photon that has a wavelength of 500 nanometers. We are given the wavelength, and we know the momentum of the photon is Planck's constant divided by the wavelength. So this one is pretty straightforward, and we end up with 1.33 times 10 to the negative 27th kilograms times meters per second. One of the most useful experiments in the early 1900s was done by a man named A.H. Compton. This Compton effect further confirmed the quantum theory of light. Compton sent shortwave X-rays at various materials and detected the light that was scattered at various angles. So the incident rays, or the X-rays, hitting the electrons would come in at some angle and some wavelength, hit the electron, and both would bounce off in some direction. What he found was that the waves produced after the collision had a different wavelength than the incident rays. The waves that were produced had a longer wavelength than the incident rays. We have our incoming incident ray that has some wavelength represented by lambda. The wavelength comes in at some angle to the vertical axis and collides with the electron. Some of the energy from the incident rays is absorbed by the electron and some of it is scattered off at some other angle. The wavelength of the scattered ray is found to be larger than the wavelength of the incident ray, and this is what is known as the Compton effect. The wavelength of the scattered wave is found by the given equation, where lambda is the wavelength of the incident ray, h is Planck's constant, me is the mass of the electron, c is the speed of light, and phi is the angle of the scattered ray. A little rearranging gives us the expression for the change in the wavelength, which is known as the Compton shift.